Okay, hi everybody. State the comparison test. And then prove it by applying the monotone convergence theorem. Okay, so if we have infinite series, let's say some of the ANs and some of the BNs, these are infinite series over, n in some, maybe the natural numbers, maybe the positive numbers. We don't really need to specify. What's the comparison test say? Well, if we have these series and they're all non-negative and all the BNs for all n, if this holds, in other words, each term is bigger than each term here, and they're all non-negative, then what? Then if the smaller ones diverge, so do the bigger ones. If the bigger ones converge, so do the smaller ones. If the bigger ones converge, then the smaller one converges too. Okay, because basically the bigger ones are going to bound the smaller ones. I guess I can get rid of this if. Let's call this statement star, and then the second statement is logically equivalent. We say not this, implies not this. Okay, what does this mean? Well, this means that if the smaller ones diverge, well, then the bigger one probably diverges too. Okay, and in fact, not probably, it does. And now let's prove it. Let's prove it by applying the monotone convergence theorem. So I'll switch color. So part B. First note that 2 is the contrapositive of 1, of star 1, or of 1 star. And you don't have to use this word, but it's good to know it. You could just say that, instead of using a fancy word, you could say that the second statement is logically equivalent to the first. You do need to know that this is the case. So in other words, if 2 is the statement P implies Q, then 1 is the statement that not Q implies not P. Okay, and these are logically equivalent. And so what's the punchline? So we only need to prove the first statement. If we prove the first statement, automatically we have proved the second statement too, because they are logically equivalent. Okay, so here's my proof of star. So I have to prove this. Now, to help my reader, I'm going to remind my reader what I'm doing. So assume that the sum of the BNs converges. Okay, we need to prove what? I'm just helping my reader understand what I'm about to do so they can actually understand my words. We need to prove that the a sub n's converge, that this infinite sum converges too. Okay, the strategy, we will use the monotone convergence theorem. Applied to the sequence of partial sums. So we want to prove that the a sub n's converge, so let's look at their sums. Let's define s sub m equal to a1 all the way up to am, this partial sum. So to apply the monotone convergence theorem, we need to show that s sub m, this sequence of partial sums, is monotone, either increasing or decreasing. This one will be increasing. Because, why? Because the terms are non-negative. So when we add a new term, it gets bigger. That's why it's going to be increasing. And the monotone convergence theorem needs monotone increasing and bounded above. And bounded above. Okay. Okay, so if we can show this and this, we are done. We are done. First, since 0 is less than or equal to an for all n, we know that s sub m and s sub m plus 1, in other words, we added a non-negative thing, so the partial sum gets bigger. Hence, the sequence is monotone increasing. And we have already finished this one. We're done with that proof. Okay? As needed, right? Now, to show bounded. So this kind of thing, like this sentence is super important because it's going to help your reader understand what you are doing. Okay? So I'm just telling the reader like, hey, now I'm going to show that it's bounded so that the monotone convergence theorem applies. So I'm just telling the reader, now let's show bounded. Okay, so how do we show bounded? How do we show that it's bounded? Well, what's bounded? Well, the sequence of partial sums is bounded. And I guess this is where we use this part. Okay? And in fact, we use that, we know that this sequence converges. Remember, we assume that the b sub n's converge. Okay, so since the sum of the b sub n's converges, their partial sums, well, okay, we already called these, the partial sums of the a's, we call them s, so let's call these t's. Tm is just the b1 plus all the way up to the bm. So their partial sums of these b's converge, right? That is the definition of an infinite sum converging. It means that their sequence of partial sums converge. Hence, the t sub m's are bounded. The t sub m are bounded. Because we proved that before, that a convergent sequence is bounded. Call the upper bound u for upper bound. It's a real number. And that just means that the t sub m's are all less than or equal to u for all m. Okay? But then, so here's what I'm going to do. The s sub m, we would like the u to be an upper bound on the s sub m's as well. Okay, so we'd like s sub m something less than or equal to u. Because then we have showed that the s sub n's are bounded, which is what we need. Okay, so this is what we're going to do. Well, what is s sub m? S sub m, by definition, is this partial sum. But then we have this, which is by definition t sub m. And we're done. Now, this equal sign is the definition of t sub m. This equal sign is the definition of s sub m. We need to justify this less than or equal to sign. And that is our last assumption, that all the b sub n's were bigger than the a sub n's, and that's why it's true. Okay, and we're done. So now it's your turn. Quiz yourself. Can you even remember what the problem statement was? Can you remember that? Just go to a blank sheet of paper. What was the problem even asking you to do? Don't look. Rack your brain. That means like think hard about it. You're not going to get it at first. What was the problem about? Just write down what the problem was even asking you to do. Then, can you prove it? can you first state it, and then can you prove it? Okay. This is important. So set 30-minute timers and just do this repeatedly. Quiz, look at the answers, quiz yourself. You didn't get it again, look at the answers. Maybe you can get it this time, quiz yourself. Then look and you made some mistakes. Or maybe you look and you see, oh, I got it. Hooray.